Well, friends, I have been defining a number of terms during course of my lectures. Previously, I have defined what is waste, what is industrial waste. We have seen what is meant by pollution, what is meant by air pollution. And in the last lecture, I introduced the term ecologically sustainable development. It is an extremely important idea. Whatever development we are talking about has to be now ecologically sustainable development. And the simple idea behind that is we need to have development which meets the need of the present generation without compromising the ability of the future generation to meet its own needs, and also improving the quality of life while living within the carrying capacity of the supporting ecosystem. I have also given you the idea of what is carrying capacity. Any environment, natural environment, can take pollution only up to a certain level, and it has the inherent capacity to find remedial measures for it, but there is a limit beyond which it cannot do so. Now, few years ago, when Dr. Murli Manohar Joshi was the education minister, HRD minister, he had talked about a term called sustainable consumption. Means he tried to say that your consumption levels can be up to a certain limit beyond which it cannot be sustained. So, obviously, consumption can be sustained only if your development is sustained. These two terms are related, but that term sustainable consumption has not caught on, at least in scientific circles, but there is a merit in it, and maybe I will refer to that little later about sustainable consumption. Now, regarding the carrying capacity, let me mention one or two more things, and that refers to what we call this diagram. You see, the economic progress which actually attempts to improve the quality of life comes from, as I mentioned, availability of goods and services. So, from resources that we have, there will be input, there will be activities, maybe manufacturing activities, service activities, there will be an output, and that will go towards quality of life. But these activities also generate wastes and residues which will go to the environment. So, from the resources we are generating goods and services as outputs for better quality of life, but during this process of making available goods and services or various activities, we necessarily generate wastes that go into the environment. Now, there is a supporting capacity for these resources. Some resources are renewable, some resources are not renewable. For example, suppose we take out from the forests timber for some activities, a timber based industry. Now, we know there is a supportive capacity, that the forests continuously generate trees, trees grow, they continuously generate timber. It has a supportive capacity. From a given forest, you can take out periodically certain amount of timber. If that amount of timber is also being generated, then you are matching the supporting capacity. If you take out more timber periodically than during those periodicity not enough timber is being generated, then you have exceeded the supporting capacity of the supply source. So, there is a concept of supporting capacity which should not be exceeded. Unfortunately, some resources are not renewable, like if you have mines and from which you are taking out ores and minerals, the mines do not have the supporting capacity to replenish them. They cannot make their own ores and minerals. If we are taking out oil or coal, there is no supportive capacity to fill up the coal seams or the oil reserves. So, they are non-renewable resources, but in the case of renewable resources we have a supporting capacity. More important is what happens to the environmental side. The environment is what has an assimilative capacity. If you reject wastes which are below the assimilative capacity of the environment, then there is no problem. You have a sustainable development activity and it can go on. But if you are discarding to the environment wastes which exceed the assimilative capacity, then you have a problem. Then there is a mismatch between supportive capacity and assimilative capacity. So, this is the concept of regional carrying capacity and capacity based development planning. Let us consider another term, it is called life cycle assessment. It is also a very important term and it is also part of industrial metabolism. Life cycle assessment or LCA is a technique for assessing the environmental performance of a product. We are now going to see the performance of the product in relation to the environment, or it can be the performance of a product, performance of a process and policy or any activity from cradle to grave, that is from exploration and mining of raw materials to their extraction, use and final disposal. You have to consider the entire range from extraction to final disposal, and it may be noted that emission wastes arise because of because the efficiencies inefficient causing losses in both material and energy use. If there are losses in material and energy use, then you have a problem. Now, life cycle assessment will have to take into account from cradle to grave. I will come to that little later. Now, let me see now how the regulatory authorities today employ a procedure for environmental review of industrial projects. There was a time when if an industrialist has the capital, he could buy land, he could buy machinery, he could hire people, he could set up an industry. Nowadays, this is not possible, because the government has regulatory bodies with people who are very well aware of the environmental issues. They would not like to support, if they can, things that are going to have adverse impacts on the environment. So, the entire procedure for approval of a project submitted is like this. To start, there is submission of project questionnaire by the one who gives the proposal. First, he has to fill up a questionnaires giving answers to many questions of relevance to environment. This will be reviewed by Pollution Control Board. They will try to find answer to this: is environment management plan satisfactory? If it is satisfactory, it will go to the next step. Can issues, sorry, yes. Then the question is that there are many issues raised, can the issues be resolved if there are problems? If there are no issues, if there are issues that cannot be resolved, it is rejected. So, the board will first see whether it is sound from environmental management point of view, and if there are tricky issues, there are suggestions as to how to solve them, then only it moves. In case there are no tricky issues and it is environmentally sound, this question is not arising, then it will go straight yes, it will go to next step where there will be issue of no objection certificate by the State Pollution Control Board. They will take into account what effect it has on the water body, on the land, whether it has effect on the on the surroundings, all kinds of things are there. Now, if there is no, then there is a no objection certificate from PCB and they will be reviewed by state PCB, and they will raise the question, does the project conflict with existing policies and plans. So, at every stage they will review whether there is anything that contradicts the environmental plans the state has. If there is a no, it will be rejected. If it is yes, it will move. If it is no, then other questions come in, like if it is no, it is rejected. If it is yes, the question will be, is project site acceptable? The project may be okay, is the site acceptable? If it is yes, then is project thresholds satisfied? All kinds of questions. It is only when yes, there will be an environmental clearance. If there is no, somewhere if it gets stopped, like questionnaire returned to the proponent with the recommendations for review by the board. Sometimes it is rejected straight away, sometimes they have seen that there can be suggestions based on which things can be improved. Then it has to go back again and start all over again. Again it will be seen by those who submit the proposal, it will be submitted, project questionnaire and scoping report by proponent of MET. Again there will be a review, it will go to referees now, then there will be another review. Review, is the comprehensive environmental impact assessment required? Sometimes you need an impact assessment. If it is yes, it will go for some more steps. If there is no, it will go straight. The final question, is the project acceptable? Can issues be resolved? If it is no, it is reject. There will be some recommendations and finally, there will be environmental clearance. The idea of saying this is that our governments in every state has become far more careful now. There are many steps in the review process. This thing is now being modified, because in some of the review steps they also bring in what we call stakeholders. They might like to have a representative from the location where the project is proposed. They may have to have representatives from, if it is a tribal area, representative of tribals to see what their views are. They might bring in NGOs which are active in opposing on environmental grounds projects. So, they are all stakeholders, and that is how one has to proceed step by step very cautiously. Now, at this stage, because essentially all developmental work depends on exploitation of natural resources, I would like to give you a very beautiful quotation by Frederick Soddy. The quotation is here: civilization as it is at present, even on the purely physical side, is not a continuous self-supporting movement. It becomes possible only after an age-long accumulation of energy by the supplementing of income out of capital. Its appetite increases by what it feeds on. It reaps what it has not sown and exhausts so far without replenishing. Its raw material is energy and its product is knowledge. The only knowledge which will justify its existence and postpone the day of reckoning is the knowledge that will replenish rather than diminish its limited resources. Our resources are limited. So, we need to have the wisdom to know not to diminish what we cannot replenish. The other issue that we have to keep in mind is not a quotation, I have written this, is that energy and environment both are intimately related to the development activities, for which the exploitation of natural resources is a must. There is no alternative to this. Interestingly, the two of the fossil fuels, coal and petroleum, are benign wastes produced in nature, as I mentioned previously. Nature does not process them further, and by exploiting them, we might have done something unnatural. In nature, they are not processed further, nature leaves them as it is. But our civilization development starts where nature has stopped. So, maybe we have done something very unnatural, and when you go against nature, we might be fighting a losing battle. Now, here is something again philosophical, a soft subject, but I thought I will mention it. You know, we go through in our generation of knowledge and wisdom through these steps: data organized is information, information distilled is information knowledge, further distilled and processed it becomes productive knowledge, that is wisdom, which tells us how to act. So, from data to wisdom we go through certain steps, and which is characterized by increasingly indiscriminating and utility, or in increasing understanding and utility. We need more understanding of data to have information, more understanding to make it into knowledge, more understanding to come into action for utilities. Now, what does data involve? Grouping, classifying, relocating, formatting, signaling, displaying. This is an organizational step. As we go up, we need separating, evaluating, comprising, interpreting, synthesizing. So, we are creating information out of this. It is an analytical process. Then there is a judgmental process, presenting, considering options, advantages, disadvantages. Then there is a decision process, matching goals, compromising, bargaining, choosing. There is increasing noise here. So, actually filtering out noise, things that we want to go towards less noise when we go for final action. So, this you remember, it is a very complicated process. We need to be wise for sustainable development. And as regard wisdom, there is a very famous saying by Marcel Proust that we do not receive wisdom, we must discover it ourselves after experiences which no one else can have for us and from which no one else can spare us. The knowledge we have today, our predecessors did not have. We cannot get the wisdom to solve the problems of today by looking at the texts available earlier. We have to find it for ourselves, and if we do not, nobody will spare us. Now, let us become a little more technical, leave aside philosophy. What is development? I will repeat again. Development is availability of goods and services for all sections of the population. There is a recently a book has come out, made a name, is called the bottom of the pyramid. You can have a development where the pyramid top is very high, but at the bottom of the pyramid, the people who are there, that forms the base. You cannot have a nation developed only at the top, not developed here. We have more than 500 million below poverty line. We have 300 million illiterates. They are at the bottom of the period. They have not seen the development. And development is not necessarily highways, flyovers, tall buildings, gadgets, consumer items, clubs, disco joints, pubs, swimming pools, shopping malls, automobiles, aeroplanes. These are important, but also important are the goods and services made to the other sections. Progress and development is demanded by the population. This needs more production, which needs energy. Progress generally leads to more pollution, and all the P's are related. You have the population, which needs progress, that needs production, production leads to pollution. The so-called progress, if not monitored, can lead to problems, poverty from unbalanced growth, petty pressure politics, pessimism, prediction of doomsday, all kinds of P's. And progress with peace and prosperity demands plans, prioritization, public participation, people's power, pragmatism. So, there are all kinds of P's in this process. We know the problems. Where is the solution? And these solutions will have to be kept in mind when we want to attack the problems of non-ferrous metals industry from the points of view of energy and environment. Lots of R's will give us solution for all the P's. R, 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 R. R for reduce, control industrial metabolism, cut down input of materials, then output of materials in terms of wastes will also be minimized. 1 R for recover, recover as much as you can during the processing steps. 1 R for recycle, go for secondary metal production. R for reuse, you may not recycle the whole things, but try to see is there something you have produced that can be reused. R for resource, restore resources if you can. If you take out minerals from the mines, you may not be able to restore it, but you should not spoil the topsoil, the overburden, that you can restore. If you are carefully planning things, take them aside, then put them back on the mines. We need to discard obsolete technology, we need to use improved technology, we need to improve control, we need to utilize waste, recycle. This is valid for both energy and environment. A simple example, the copper industry at one time when it was traditional, it had the traditional roasters, then reverberatory smelting, then converting. In those steps, all kinds of heat were wasted because you went from one step to another. Lot of SO2 were emitted, about which we had no solution, but when you brought in flash roasting, we combined roaster and smelters. The next step was continuous copper production, where we cut down the stages. So, we cut down the total heat requirements. The whole process was autogenous anyway, it was generating heat. It was used much better when there was one reactor, and if all the SO2 coming out were coming out in one stream, it could go for acid production. Instead of little SO2 at the roaster, some at the smelter stage, some at the converting stage. If everything happened in one reactor, things were much better. So, an improvement in technology helps solve many of the problems. There are many such examples in non-ferrous metallurgy. What we mean by the word reuse? From an environmental perspective, energy savings are only one of several important considerations in recycling. When you talk about reuse or recycling, our natural tendency is to always think in terms of materials being reused, recycled. No, it is true in terms of energy also. energy that is coming out of in pyrometallurgical processes, can you reuse it instead of allowing it to go into the atmosphere? Can you trap that energy? Not only that, when you are discarding hot solids or hot liquids out of a reactor, there is sensible heat in them. If you leave it into the environment, as it cools down, all the heat is dissipated, lost, and they are of no use. Can we recapture that heat? There are technologies available for getting that sensible heat, or if there is a gas coming out which can undergo combustion and give you more heat, that is even better. Like the blast furnace gas, the CO that is in there, can it undergo combustion, give you more heat? It can, because blast furnace gas it is not a very high calorific value gas, but it has calorific value and it is used in the plant in many sites. Now, in many cases there is a trade off between reduction in energy consumption and that of water and air pollution, as well as in generation of solid hazardous wastes. So, we often have to go for a compromise and trade off. For example, there is a trade off that we can reduce energy consumption and that of water and air pollution, and maybe allow little bit of solid hazardous waste, or we bring that down and use little more of these. So, this kind of a compromise which is ultimately good for all, we have to go for. In some situations, product reuse or material substitution may be more desirable than recycling. Maybe recycling is not required. We will use the product as it is, reuse, or we will have a material substitution. Today's society demands a product that saves the most energy if recycled. Today's society demands product that saves the most energy if recycled, but rather I think product that society demands there should be not the product that saves the most energy if recycled, but a product that has the lowest overall environmental impact. What does it mean? I will give you some example. In our industrial consumer oriented society, the focus is always on what to do with waste after they are generated, rather than how to prevent generation of waste in the first place. Let me give some examples I think I have to explain this. Before that, I have a very nice quotation from Buddha about reuse. I will read it. Shyamavati, the queen consort of King Udayana, offered 500 garments to Ananda, the favorite disciple of Buddha, who received them with great satisfaction. The king, hearing of it, suspected Ananda of some dishonesty, that how can a monk be so satisfied with a gift of 500 garments. So, he went to Ananda and asked what he was going to do with these. He said, O king, many of the brothers in the order are in rags. I am going to distribute the garments amongst the brothers who do not have proper dresses, garments, they are wearing rags of now. What will you do with the old garments? The king asked. We will make bed covers out of them. What will you do with the old bed covers? We will make pillowcases out of those bed covers. King asked Ananda, what will you do with the old pillowcases? We will make floor covers of them. What will you do with the old floor covers? We will use them for foot towels. What will you do with the old foot towels? We will use them for floor mops. What will you do with the old floor mops? The king asked. Your Highness, we will tear them into pieces, mix them with mud, use the mud to plaster the house walls. House walls will be stiffer and better. This is the about reuse. Nothing is going to waste. This central philosophy of this quotation is to tell you, if we are smart, we will use everything, because there is always a use, if only we know how to use that material. Now, this is also a kind of cascading that one thing goes into the other. Waste energy has both quantity as well as quality, you should know that. You may have a whole lot of energy coming in out, but if the temperature at which the gases containing that energy is low, according to the second law of thermodynamics, it is very difficult to extract energy out of that. A simple example, you can boil a cup of tea by using a candle, because the candle has a flame which has a temperature much higher than the boiling point of water, and it can boil the water. But if you put a glass of water in the in a sea, the entire sea has lot of energy, but it does not have temperature. It cannot boil that tiny the small amount of water in a cup. It cannot, because there is heat of great magnitude in the total sea, but the quality of heat is low, the temperature is low. So, they are both important. We have to be very smart to see how to look at the quality of heat to find its application. If you go to mines, mines the coal often catches spontaneous fire. There are reasons why it does so. So, the coal mines, the holes are often flooded with water to keep the temperature cool. You pump in water, the water comes out, it is fairly hot, it is 60, 70, 80 degrees. What is the use of that water? We haven't found. What we do in our country is just throw it out. In a cold country where there is the coal mines and they have to do the same thing, if the hot water is coming out, they can find a use. They can put it on roads where there is snow, the snow will melt, the road will clear, because the quality of heat in that water is good enough to melt snow, where the melting point is much lower. In our case, the quality of water is of no use to us, because we haven't found a use for it yet. So, the utilization of waste energy can be cascaded, that it can be put to gradually lower temperature usages, like in the case of, as a cold country, it's going to use for melting of this. Now, suppose there is a hot gas coming out at 1000 degrees. It cannot be used to melt any metal or alloy which requires temperature of 1100 degrees, but it can be used for an operation where temperature requirement is less than 1000 degrees. Obviously, the efficiency will depend on the temperature difference. Utilization will be more efficient if the requirement of temperature is much lower than 1100 degrees. There is a simple equation for that. But if we can find a gradually lowering levels of temperature requirements, then we call it cascading of energy. Theoretically, one can estimate the gross available heat, and from that we can also calculate the efficiencies of such energy use. Now, let me say something again on ecologically sustainable development and some philosophical interpretation of that. The definition you have seen, development which meets the need of the present generation without compromising the ability of the future generation, and another, improving the quality of life while living within the carrying capacity. Now, if we define development as availability of goods and services, then it is a function of three things: raw materials R, technology T, and ecological support, carrying capacity, or S. Now, this R, resources, very often are not finite, even though they may look finite. People say that R is very often a function of technology. What does it mean? 100 years ago, an ore body of very poor grade perhaps was not considered a resource. We did not have a technology. But with improvement of technology, that ore body becomes an ore body from which we can get metallic values. Today, we do not consider seawater to be a resource of gold, but if technology improves, we will get a new resource of gold in the form of seawater. So, people say that the availability of resources are actually is a function of technology, and so is the ecological support. We find that we are creating environmental problems, we are not getting ecological support for a process, but suppose we improve the technology, we know how to clean up the environment, how to handle the adverse impact, then we may be able to find that yes, we can increase availability. So, eventually what happens is resources actually are a function of technology, ecological support is also a function of technology. So, many people have argued that our development can continue, availability of goods and services will go on increasing because it is only a function of technology. As knowledge advances, as new technologies come, we will find newer and newer resources, they will never be exhausted. We will find newer and newer methods of finding solutions related to ecology, if only we go on improving knowledge and technology. So, we do not have to worry. So, many scientists even are divided now into two camps. One are the optimists and one are the pessimists. The optimists argue like this, that go on acquiring knowledge, go on advancing your technology, you can find solutions for all problems, there will be no dearth of resources, there will be no dearth of techniques to handle environmental problems. But there are others who want to be more pragmatic. Some of them are called pessimists. They say, look, T cannot be infinite, knowledge cannot be infinite. You cannot go on increasing your knowledge and technology. There has to be a tapering off, and A cannot go on increasing. You cannot keep on making available more and more goods and services like the capitalist philosophy. I am not against capitalism, I am only against moderation. So, this relates to Dr. Murli Manohar Joshi's of sustainable consumption. At some point, you have to say you should not or you cannot consume more than this. If you do, it is not sustainable. You cannot get more and more knowledge, more and more technology. Even if you do, it will be a diminishing return. The amount of efforts you have to put in for a marginal improvement would become more and more. So, we are almost reaching a plateau. See, the advanced countries thought they can go on in having more cars, more planes, bigger houses, everything. All that has landed us into a crisis today. And they are now deciding in Copenhagen, they will limit 2% average temperature rise of the planet, and after 2020 it has to come down. And that means huge reduction of the energy consumption in the advanced countries in relation to what they were doing 10 years ago. They have to not only consume less as of now, they have to go on reducing so that go to a level which were there years ago. The countries which are developing, they are arguing, their industries are growing. They were underdeveloped one time because of the developed countries. So, they should be allowed to develop. They should be allowed to increase the CO2 emission, but at a lower rate. They argue that, so that eventually per capita emission becomes everywhere the same. Again, I am coming back to the central problem. You must understand what are the issues that divide today as they divided in Copenhagen. The advanced countries are claiming, do not go back to history all the time. You cannot reopen the issues as to why the Europeans went and settled in America or in Latin America. They cannot come back and give the land back to the natives. They said, no, you cannot go back. So, the underdeveloped countries' argument that we are underdeveloped because we were colonized, we were not allowed to be developed, our resources went for development of developed countries. So, the developed countries have to accept that as of now the developing countries which are struggling to develop, they should be allowed greater generation of CO2, but of course, at lower rates because they must efforts, so that everything should be decided on per capita basis. Now, that is where the advanced countries are not agreeing. He said, no, we are all same under the sun. India is a country, China is a country. Actually, if you go by the total emission, India is fairly large, 5th. Highest is America, by far the highest. China, 2nd. But if you go by per capita basis, I will give you the data later, USA is way above, India is very low. So, India has a right to increasing CO2 emission at least for some time until we have come to certain level. But all this boils down to the concept of sustainable consumption. You have to cut down your consumption. So, now in America there is talk of not using dryers for drying clothes. They said, why not go in the fields like the Indians do, hang your clothes to dry on the poles, on the ropes on the poles, which means they have to seriously think of going back to a simpler way of living. Okay. Now, I had mentioned this word life cycle assessment. Normally, we have been ignoring it in metallurgy or in the industries. Why do we ignore facts? Because they are not widely understood. The importance is known, but not understood properly. Sometimes facts are ignored because of other priorities and narrow visions. Now, there are 3 stages in every life cycle process. Again, life cycle means from cradle to grave, from when the product or the process took birth and when it finally died. We have to think of the entire life and not just the production stage. That will be a very narrow way of looking at it. Life cycle inventory analysis, which considers inputs for production, emission and pollutants throughout the life cycle, not just during the production. Life cycle impact analysis, which can be quantitative, it can be qualitative, and there is life cycle involvement analysis, which aims at minimizing the adverse effects of that product or services all throughout the life, not only at the time of production. Life cycle assessment is a technique for assessing the environmental performance of a product, a process, policy or activity from cradle to grave, that is from exploration mining of raw materials to their extraction, use and final disposal. I am repeated what I had mentioned a little while ago. It is defined as an objective process to evaluate the environmental burdens associated with a product, process or activity by identifying energy materials used and wastes released to the environment, and to evaluate and implement opportunities to affect environmental improvements. When you have created a product or given a service, it has an environmental impact even beyond when it started. That cannot be ignored. That is taken into account in life cycle analysis. Here is a simple example. Replacing a 75 watt incandescent lamp with an 18 watt compact fluorescent lamp yields the same light for a duration nearly 13 times as long. It keeps 1 ton of CO2 and about 9 kg of SOx from being emitted by coal fired station, because it is consuming less electricity. This also generates net wealth because the new lamp saves more in utility bills and replacement lamps and the labor to install them than it costs. Saving electricity is cheaper than making it, and pollution is avoided not at a cost, but at a profit. Now, here we are talking about a longer subjective vision. Different way I am looking at it. You might buy something at a higher price. At that time, it cost you more, but look at its service throughout the life. I will have a better example later. How much it is costing in maintenance, in electricity bills, and until it is finished, what was the overall cost during the whole life cycle? Cost not only in terms of electricity bills, because it was consuming less electricity, overall how much CO2 it has saved at the source. So, these are unusual way of thinking. There is to be an advertisement in the TV where it shows that to save electricity is to generate electricity or something to that effect. I do not know exact wordings, but the meaning was if you are saving it, actually you are creating it. Let me see, look at it from another angle. Suppose in olden days, when we had coal fired locomotives, coal in our country is found in only one corner, the eastern corner, and that coal had to be transported all over the country. It is now done being bit indirectly because from coal electricity comes and then that is going all over the place. But suppose we think of only coal being sent all over the country. Now, to transport 10 tons of coal all over the country will consume about 5 tons of coal. So, when you have delivered at different thermal power stations, you have ended up with only 5 tons of coal. And when power is generated in thermal power plants, the efficiency, if we assume 25%, you are left with actually 1.5 tons of coal equivalent for that energy. When you transmit through the lines, this 25% loss, sometimes it is 30%, 40%, because there is theft. Ideally, it should be less than 10, but assume 25% loss. So, what the energy you are getting in transmission lines is equivalent to only 0.9 ton of coal. When it goes into devices, even if they are good with about 80% efficiency, the electricity you are using is equivalent to only 0.7 ton of coal, which has come from 10 ton of coal. Do you understand how many losses we have had in the steps? So, if you save 10% electricity here, you save 10% coal at the source. So, the effect of saving is actually much larger than what you think. Now, coming back to that bulb example, I found a very nice example. You might wonder how this relates to non-ferrous extractive metallurgy. These are the ideas which can be implemented anywhere, including non-ferrous extraction processes. That is why I want to emphasize. Look at this interesting example from National Geographic, March 2009. An incandescent bulb, the olden bulbs used to have yellow lights. In the US, it costs 65 cents, in India it costs about 6 rupees. Its efficiency is only 6%. 94% of the heat goes, 90% of the electricity goes into heat. That is why it becomes so hot, the bulb as well as the holder. Now, there it lasts 1000 to 2000 hours, and it will cost 72.55% dollars in 15 years of electricity. The electricity consumption is this, because the efficiency is low, 94% being dissipated at heat. Now, if you spend more money and spend $4 and buy a CFL bulb, which has 25% efficiency, it will last longer, 6000 to 12,000 hours, and in 15 years it will consume total electricity of 18.14. So, you will be paying $3.5 more when you buy it, but your electricity bill in 15 years is going to come from 72.55 to 18.14. So, you see, if you have a longer subjective horizon, you know the benefits you are getting. Now, if you go to LED lamps which are being developed now, they will operate at about 50% efficiency. They cost $120 a bulb, last 20,000 to 50,000 hours. In 15 years, the electricity cost will be 9.67. So, in 15 years, of course, it is marginally more expensive compared to others, because to start it you spend more money, but this money may come down with development and it lasts even longer. So, you have an advantage. So, this is the kind of analysis we have to do for life cycle assessment. And please remember this, which bulb in 15 years has emitted more CO2? Obviously, the one which is operating at a much lower efficiency. On the whole, it will be consuming a lot more electricity, generating a lot more CO2. So, you have to look at things with a long subjective horizon. I will end this lecture by just mentioning the term end use analysis, which focuses on function of a product and ways to maximize total material use and efficiency, a kind of industrial metabolism. Like, the function, you want a packaging material. What is the function? To provide consumers with a convenient and attractive carrying device that will protect a product during journey from the manufacturer to the consumer. The question now shifts from how much energy is saved if the packaging material is recycled. You do not stop at this, that I have made a packaging and sent to the consumer. Think of the end where it will be recycled. So, the question now, how much energy is saved if the packaging material is recycled, we shift to a question, what is the most energy efficient method of providing shoppers with a carrying device that is economical, marketable and practical? The result of an end use analysis may well conclude that a reusable cloth bag provides the most energy efficient packaging device. So, think of things from different angles. How can we minimize material flow? How can in the total life cycle have the minimum impact on the environment? If we take into account all this, then we talk about life cycle analysis. So, now during the last 3-4 lectures, you have learnt many definitions and some explanations. We have talked about waste, industrial waste, pollution, industrial pollution, sustainable development, sustainable consumption, life cycle analysis, end use analysis. Whatever I have said is perhaps can be explained better, but at least you know the terms and you can read up on them, learn more for yourself. You should be familiar with these terms, because when you go to an industry, non-ferrous industry, ferrous industry, wherever, these things should be in your mind, because the concept we are discussing are all applicable in a manufacturing process, also for the metal extraction industry. Thank you. We will continue with our discussions on issues related to energy and environment. friends, I am reviewing the entire course, and we just discussed Ellingham diagrams and explained why the free energy plots, free energies of formation plots for oxides go this way and the slope is negative for CO. In case you wonder why the slope suddenly changes for these lines, it has something to do with a phase change, something solidifies or volatilizes. This has been discussed, so I will not discuss that again. Now, regarding the various steps in pyrometallurgy, we can consider roasting, smelting, etc. There has been, I have discussed a lot of things. I have said there can be so many kinds of roasting reactions, where we talk about converting sulfides to oxides or sulfates or lower oxides, and all these, there have been many examples of this. There are also free energy diagrams for metal sulfides. Then I have discussed the predominance area diagrams that show which phases will be stable under different conditions of PSO2 and log PO2. Starting with a sulfide, we can make the sulfate, we can make the oxide, we can make a lower sulfide, we can make the metal, all depending on the phase stabilities. And I have also indicated how we can draw these diagrams by taking into account different reactions. This is the hearth roaster, which is commonly used for roasting, where the feed goes through one hearth to another, and these rotate, and because of rotation the some hearths are stationary. On this there is a rotating device, and they throw them from one to the other, and they are all sloped. Later it was found, actually it was during the falling of particles that maximum oxidation took place. So, the idea for a flash roaster came, that instead of bothering about passing the sulfides from one hearth to another, why not just drop from the top the concentrate and air, and you get at the bottom the calcine. It can be done. Then there is a sintering machine where also roasting takes place in a continuous manner. Then you have talked about smelting, blast furnace smelting, as is applied for iron making. This can be applied for lead. We have talked about reverberatory furnace, where reactions occur over a long time. We can produce matte, which is a mixture of sulfides and slags. Then we have talked about reactors where one combines roasting as well as smelting. So, initially we thought of flash roasting, now here is a flash smelter. After roasting, it goes smelted also, and again we can directly produce matte and slag. We have discussed this in more detail with reference to some oxidation reactions, the application of the Ellingham diagrams, and how we generate these stability diagrams. I would not go into all this. I have given an example of application of vacuum, when vacuum is required, and you can calculate what kind of vacuum we need for a reaction to happen, which normally will not happen. See, normally for reduction of this, free energy change is positive, but if we can remove this CO, application of a vacuum, then we find that equilibrium partial pressure is this. So, below that pressure of PCO, the reaction can be made possible. We have talked about thermit analysis, thermit reaction, analyze that. we have talked about a similar reaction which we will call now metallothermic reduction of calcium reducing TiO2, and then I mentioned that we can write a chemical reaction like this, but sometimes in metallurgical operation this will not be accepted, because calcium as a reducing agent would become gas at the temperatures where this should happen. So, it will require a bomb or a closed chamber. Titanium melts at 1670 degrees, calcium boils at 1492, calcium oxide will melt only at 2600 degrees. So, there is a mismatch of melting points and boiling points. This sort of thing will not form the basis of a metallurgical operation. We came to hydrometallurgically, saw the advantages, and I mentioned is ideally suited for lean and complex ores. There is greater control because things are happening at low temperatures, room temperatures very often, or slightly elevated temperatures, but they are it is easy to control because things are not happening far too rapidly. Environmental problems coming out of gaseous emissions are not there. We do not have to depend on coke as pyrometallurgical operations very often depend on. It is becoming a costly reducing agent. There is no question of CO2 emission. It does not mean all hydrometallurgical operations are very clean environmentally, because many of the operations also reject slimes, they reject effluents which are also not good for the environment. Metals can be produced in a variety of forms, not liquids of course, but the solids can be in crystalline form, in powdery form. Sometimes we can even produce particles of given shapes, as we do in the case of nickel, when you reduce nickel amine solutions by hydrogen. There are some basic disadvantages which I have already mentioned, that we are dealing with dilute solutions. We need lot of plumbing, pumping, there is tremendous amount of space is required, there are corrosion problems, reagent costs, equipment costs are high, effluents can create problems. Now, essentially in hydrometallurgy we need a concentrate which will be leached. During leaching, generally we take the metallic values in solution and the gangue is rejected in the solids, but opposite of that is also done. We saw in the case of monazite leaching by alkali in our country, alkalis dissolve away the undesirables, the desirable part remains in the insoluble residue. In the case of aluminum, alkali leaching takes the aluminum value into solution, the titanium ion that we do not want to come in the leach liquor is separated as a solid residue. So, leaching does not mean taking metallic value in the solution, it can take the metallic value preferentially in the residue also. So, the whole idea is the agent must be selective, leaching must be rapid, should allow high concentration for rapid action, the leaching reagent should not corrode equipment, it should be economical and should allow regeneration. Now, there are a whole range of things used in leaching. Sulfuric acid is very common and acids are stronger reagents, they dissolve things faster to a greater extent, but there is also danger of dissolving all kinds of things we do not want to dissolve. Whereas, alkalis are milder reagents, but they may be safer from the view of more impurities coming into solution. And there are also during leaching many reducing agents are used like MnO2, KMnO4, FeCl3 etc. will increase the oxidation potential. The various hydrometallurgical steps I gave a flow sheet, leaching, then purification etc., and then there are some other things that you can read up. I try to show how kinetics can be applied in analyzing leaching reactions. Like here is a solid mineral surface which is reacting with a leaching medium, and we see it as the reagent concentration from the bulk getting depleted when it comes to the surface. It is coming this way. Metallic values that dissolve at the surface diffuse out into the bulk, and when it diffuse out, there must be a concentration profile going down. The concentration must be increased here. If there are some other products, residues, apart from metallic volumes which go into solutions, this would also have a concentration profile. If there is a solid porous residue, then the diffusion processes take place through that residue. Reagent has to the reagent has to come through the layer to the surface of the mineral, and the metal that is going into the solution has to diffuse through the porous residue, etc., etc. Suppose there is a leaching reaction where the intermediate residue layer is not porous, but is very adherent, then leaching reaction will stop. So, this possibility is also there. We discussed this little more from kinetic point of view, that any leaching reaction can be expedited by stirring, because there is a concentration profile at the surface and there is a concept of boundary layer, where say 99% of the concentration change takes place. So, if you stir the solution, the boundary profile is reduced, the concentration profile is made steeper, because the boundary layer becomes thinner and the stirring speed increases. But in this case, if you plot the stirring pace against rate, we find that beyond a certain stirring speed, the rate of diffusion cannot increase, because it has been reduced to the minimum, the boundary layer thickness. So, then only temperature will have to be increased. So, we have done this sort of analysis, and we have done this analysis particularly in case of cyanidation of gold. There is a surface where there are gold particles and cyanide ions are in the solution. Cyanide ions have to diffuse towards the surface, the oxygen has to diffuse to the surface, and gold cyanide that forms at the surface have to diffuse out. So, we did an analysis of that to know what will be important when. Is partial pressure of oxygen important, because that is also reactant? Is cyanide concentration important, because that is also there as a reactant? Then we analyze that under different conditions something is more important than the other. We talked about a cementation reaction, that iron filings put into copper sulphide would produce ferrous sulphate and copper will precipitate. It is an electrochemical reaction with a cathode area and an anode area. We made an analysis to understand what factors will govern the rate of the cementation process. It is not very difficult to understand. Then we have come to a very important area, and we looked at it from thermodynamic point of view, that zinc, when reacts with H2SO4, releases hydrogen, because zinc is more electropositive. We can write a general thing that a metal ion which is more electropositive dissociates hydrogen ions. Now, suppose we have in the solution nickel ions, cobalt ions, can we precipitate them out as a metal by hydrogen? Now, normally if the metal is not very reactive, obviously metal ion will not react, metal ion will not react to generate hydrogen. But if it is a reactive metal, then it will react to produce hydrogen. Then how will hydrogen precipitate from the solution a metal which is reactive. For that we have to do an analysis. We have written this reaction in the other way, that we intend to convert metal ions in solution into the metallic form by reaction with hydrogen. Now, normally, as I said, reactive metal ions cannot be converted to metal, because this reaction will predominate. But we can make this thermodynamically feasible by increasing the pressure of hydrogen, reducing hydrogen ion concentration, and try to see whether we can push it to the right. This will never be possible for say sodium or potassium or cesium and things like that, which are so reactive. It does not matter how much of hydrogen pressure you apply or how much you lower this down, which means how much acid you make, this will not take place. But there are cases which are marginal cases where this will happen, and this is the kind of analysis we have done. We have looked at, we have expressed this in terms of hydrogen ion potential, pH and pressure, and come up with an equation in terms of metal ion concentration, which is a function of electrode potential of metal, and one has to be more than the other, so that the reaction takes place. And then finally, we have got a plot which shows the variation of potential with metal ion concentration for various values of pH 2 and various values of pH. And we have shown that while normally say nickel ion will not be cannot give nickel metal, but if we go to a suitable pH value, or if you apply the suitable pH 2 value, the lines for hydrogen ion potential and metal ion potential in case of nickel and cobalt will cross. Something like zinc cannot be zinc metal cannot be produced, no matter what pressure of hydrogen you give or what is the value, no matter how alkaline it is, because it is far too above in the electrochemical series. So, this analysis we have done, we have shown the pH requirements for equilibrium pH values, and then we have shown that if you try to make something very alkaline, then also there is a danger of precipitating hydroxides. So, we said there has to be precaution taken, and one way would be to stabilize the metal ion as an amine, and we have discussed what is the optimum condition, say in the case of nickel, and discussed several other things. Then an interesting thing I have also said, that while nickel and cobalt can be precipitated from acid solutions with hydrogen ion pressure, hydrogen gas pressure under normal range, but adjusting the pH, the particles that come out can be of various shapes depending on some catalysts that we put in the system, and we have talked about some catalysts that give rise to particular shapes of nickel nuclei. For more details, you have to see the book. In module 4, we have talked about electrometallurgy and refining of metals. We have combined the two because electrometallurgy generally produces metals of very high purity. Generally, there are exceptions, and refining of metals also aims at producing high purity. So, electrometallurgy in a way is a step towards refining, that is why I have put them together. Secondly, electrometallurgy has come in the history of metallurgy much later than pyrometallurgy and hydrometallurgy, because electrometallurgy had to depend on invention of electricity. Otherwise, you would not have electrometallurgical process. We have given a classification of electrometallurgical processes. We have talked about structure of solvent media, aqueous solution fused salts where electrolysis takes place. Then we have gone into some very interesting discussion of molten salt systems and Temkin model. we have talked about principles of electrolysis and principles of electrorefining. Then you have talked about performance criteria of electrolytic cells. Here is a classification of electrometallurgical processes. Now, by the word electrometallurgy, many things are implied, but we have picked up from the entire gamut of things only this area, and that is neither this, nor this, nor that, nor this. What we have talked about electrowinning and electrorefining, only these two we have talked about. We have not talked about many other things, because they are not directly related to electrolytic processes. Electrolysis, the structure of water molecule, water is a polar molecule. So, we never have H2O, we have many H2O molecules associated because of this kind of bonding. That is how we get hydrated ions. As regards molten salt systems, they can be of many kinds, single component systems, multi component systems, and etcetera, etcetera. You will find when we talk about fused salt electrolysis, very rarely we have a single component system, always it is multi component. There are very good reasons for that. First of all, when you mix 2-3 salts, your temperature, melting temperature comes down. So, you can carry out an electrolysis or electrorefining process at a lower temperature. There are also some other reasons. Try to remember that, or else I will remind you just now. I have given you some data to show what kind of purities are obtained. You see, during electrowinning from aqueous solutions, we get purities of 99, 99.9, 99.8. Very often we have to have such purities, because unless the solution is pure, you cannot do zinc electrolysis, because zinc is normally above hydrogen. It is only in a pure solution that you can have activation over potential, where the hydrogen potential exceeds that of zinc in the EMF series. So, we need extreme purification of the zinc leach liquor. Yet, the metal you produce really is not required at that purity for most applications. Most important application are galvanizing, which will do with a lower purity, but we can't help. We have to put pure zinc. In some cases like copper, we settle for a slightly lower thing, but it has to go for electrorefining later on, because we want to recover from their precious metals. We have also given some ideas about the kind of what kind of salt mixtures we take, what kind of current density we have, cell voltage, etcetera, etcetera, etcetera. We have given you some typical data for aqueous, more data for aqueous systems for electrorefining, which is one step beyond electrolysis, and that is to produce purer copper and get some byproducts out. I have talked about this over voltage phenomenon, which changes the voltage at the electrode, either because of a concentration over potential, because when the current flows, the bulk cations are flowing towards the cathode. The flow has to be because of a concentration gradient. This gradient becomes steeper when the current increases, because there is more flow of the cations, and which means you have a steeper gradient, that is why a greater flow, but there is a limit beyond which we cannot push it further, and that is becomes rate controlling. So, there is, because of this concentration gradient, a concentration over potential, and then a limiting current, or for a given area of the electrode, a limiting current density, which limits the amount of metal you can deposit on a cathode in a given cell. Because of concentration over potential, my analysis shows that the potential of the electrode does not change so much, but then it sets a limit to production. Now, in some cases the limiting step is not concentration over potential, but activation over potential, which makes it possible to have zinc in zinc electrolysis. But then this concept of limiting current density is very important. Why it is important? Because then in a given cell we are fixed. How do we increase the productivity? For that, couple of methods are available. We can rearrange the electrodes in various manners, or you can use a fluidized bed cathode, where the effective surface area of the cathode becomes much larger. I have shown a figure of that. Before that, I have given one or two solutions, one or two problems, simple problems, of one for fused salt electrolysis, one for aqueous electrolysis. I have given some data for electrowinning from molten salts. What kind of cell voltages in this case would be slightly higher, because you are dealing with more stable salts. At higher temperatures, your current efficiencies suffer, because other kinds of reaction can take place. Your energy efficiency would be lower. Many other data we have given, but you will see in all cases the supporting electrolyte which dissolves the solute is never a single salt, mostly it is a salt mixture. Incidentally, the supporting electrolyte, the salt mixture, has to be more stable than the solute, otherwise something else will get electrolyzed from that supporting electrolyte. Then we have come to talk about the energy requirement, and we have seen that energy requirement in electrometallurgical processes will be more, in pyrometallurgical processes it will be low. We have also discussed the unit energies for production of primary secondary metals, again to show how things are different when there is a electrometallurgical operation. Because of the use of electricity, your energy consumption is very high. Steel, lead, where your concentrates are of high grade and the operation does not need too much of energy, your energy consumption is better. Then I discussed, just to show how things are analyzed, a very interesting reaction goes in the name of Van Arkel process, or we can also call it a vapor transport process, that we can take an impure metal, make it react with a gas phase to produce a second gas phase as one temperature, then decompose that gas phase at another temperature to produce pure metal. So, take impure metal, this should be plus, react with a gas phase, produce an intermediate gas, take it out, then sometimes at a higher temperature decompose to produce this, sometimes at a lower temperature it will produce a purer metal. And I have given an analysis as to how this is to be done and what are the factors that govern it, and take for particular reference we have taken reaction in case of tungsten, tantalum, hafnium. You form an intermediate chloride which will be decomposed to produce pure tungsten in another chamber. And we have shown that we have to understand the reaction in terms of enthalpy change, entropy change and melting point. Then we came to some general conclusions, that no transport of this kind is possible if the delta H value is 0, if the absolute temperature of delta H naught is very large, then too there can be no measurable transport, and it is delta H naught sign that depends the direction of vapor transport. Then there is also this element, that delta S naught, if it is not equal to 0, is a delta H, some condition regarding entropy change also. This you have to cannot be done simply. I have also talked about purification using ion exchange resin and solvent extraction, how things are done. I would not go into those. Talked about different methods of refining, separation by liquefaction, and this there have been examples of that later on. If we have impurities like lead, if you consider lead zinc diagram, you see what happens when you go to higher temperatures. We can create two liquids, one very rich in zinc, one very rich in lead. So, if you have an alloy of this composition, if you go to that temperature, will produce a liquid lead percentage so much, zinc percentage so much, and the relative proportions will depend on the lever rule. So, this is one way from a alloy we can separate out the components simply by heating. Similar liquefaction, possibility of separation by liquefaction, another system. We can separate constituents from an alloy by differential distillation. Like if we have aluminum and magnesium, if we reheat the alloy, magnesium will evaporate first, because this is the vapor pressure of magnesium. It reaches 1 atmosphere at low temperatures. Aluminum will volatilize at much higher temperatures. Okay. We have talked about vapor liquid equilibrium, we have talked about zone refining. I have talked about these things in a very cursory manner, because they are given in books, arc melting, electron beam melting, electrosag refining, these things one has to read up. Now, up to this we discussed the principles, then we came into the extraction processes for specific metals, and these were done in 3 different models: metals from oxide sources, metals from sulphide deposits, and metals from halides, not all naturally occurring halides, but naturally occurring halides, and also halides which were the starting point of some metals, and these halides may have to be prepared from oxide deposits. Talking about metals which come from oxides, and the learning objectives was basic approaches in oxide reduction, special features of specific extraction processes, and extraction of metals such as magnesium, aluminum, tin. Ferroalloys also I included in this, because they also come from oxide sources, and I have given some discussion on energy and environment related issues, which have been discussed in more detail towards the end. Magnesium we have talked about its uses, and then we have seen that essentially the process depends on dolomite decomposed to produce Mg and CaO reduced by ferrosilicon or silicon. Magnesium comes out as a vapor, and the reaction is made possible by taking out the vapor continuously by a vacuum. That is why the reaction becomes possible, and this was first introduced during Second World War by Dr. Pigeon, and that is why it goes in the name of Pigeon's process. Reducing agent is ferrosilicon. We also produce a slag, but the trick is that the metal comes out as a vapor with a pressure at a pressure lower than 15 millimeter, and that is what makes the reactions possible. We have talked about the mechanism, how it takes place. You might think it is a reaction between a solid and a solid, which is not true, because solid solid reactions cannot be very efficient. How often do solid particles come in contact with each other? The surface of contact is very small, but essentially it is a reaction of a solid with a liquid. initially the iron reduces CO to produce a liquid calcium, and it permeates the solid. A liquid calcium iron alloys permeates the solid briquettes, and that is where the reaction takes place. It is not a solid reaction. An advancement of this process is where we make everything molten by having a bath at 1500 degrees centigrade by addition of alumina to form a slag. It is called electrotherm process. Then we came to aluminum. There are many uses of aluminum, and today after steel, the most two important metals are aluminum and copper. Aluminum of course has good thermal conductivity and electrical resistivity. It comes fourth in the category. Silver, copper, gold are better than that. And the key to aluminum extraction is Bayer's process, which produces pure alumina. It depends on many factors. Some of them have been considered: particle size, concentration of leach liquor. People have come out with an equation for the rate of leaching. Temperature should be high, but they make the temperature high and sometimes it operates at 220 degrees leaching. You need lot of pressure in an autoclave. Some people would rather settle for lower temperatures, because autoclave operation at higher temperatures means more expensive equipment, more energy. So, the different companies have different ways of doing. No two companies act in the same manner. Eventually, everybody tries to produce pure Al2O3 from which will go into an aluminum cell. Now, what is the reaction? When alumina dissolves in cryolite, ideally we should try to get aluminum metal from aluminum ions and oxygen from Al2O3's oxygen part. Unfortunately, to take out oxygen as a gas, you need a platinum electrode. You can't think of platinum electrode for the surface. People are thinking of inert electrodes which will have TiO2 on the surface. It has not come in the industry yet. We use a consumable electrode which is graphite. The oxygen will go to the anode, which is graphite, and there it reacts to form CoCO2, which is good news as well as bad news. The good news is, because carbon is taking part in the reaction, taking away oxygen, it makes decomposition of Al2O3 easier and decomposition voltage comes down. So, the energy requirement comes down as compared to if oxygen was released as oxygen. The bad news is, by consuming the oxygen, removing the oxygen which reacts with carbon, you generate CO and CO2. The proportion depending on the temperature operation. Because it is 1000 degrees, there is more of CO than CO2, which is something we do not want. Now, many people have thought what to do about it. Can we inject a reducing agent at the anode, say hydrogen or methane? We have given some analysis to show there may be marginal advantage, but there is no technology for doing such things. Ideally, we should go for an inert electrode where there will be no carbon consumed, no CoCO2, but then you have to have higher decomposition voltage, which means more energy, which means somewhere else you are producing, you are consuming more electricity. So, you have to balance this. The amount of CoCO2 you are saving here, is it more than amount of CoCO2 you are releasing at a power plant from which you are drawing power for electrolytic solution. I have given you a sketch of the aluminum electrolysis cell, aluminum anodes, and this is the cathode. this cathode eventually gets poisoned, and when this cathode is thrown out, nobody knows what to do with that waste cathode, because it is full of fluorides, and as of now it is only dumped. This electrode, carbon electrode, gets consumed. So, it has to be changed from time to time. A fresh one is brought and screwed on, or there are today Soderberg electrodes, where a carbon paste is continuously sent down through a pipe, and the paste gradually solidifies and is come to high temperatures, and it becomes the anode, but it is consumable. The trick here is, we have aluminum at the bottom protected by the electrolyte, and there is a crust of L2O3. That is how the process occurs. There are equations as to what all things affect current efficiency. Then we have said it is not so simple an reaction during electrolysis, that L2O3 decomposes to aluminum and oxygen goes and reacts with the carbon anode. It is not so. All kinds of things take place. There are all kinds of anions existing there, and because of their existence, there is evolution of fluorine gas, there evolution of other gases that you do not want. Not only they cause contaminants in the environment, they also bring down the current efficiency through undesirable reactions. Now, a lot of attempt has been made over the years to bring down the energy consumption, and the energy consumption has come down. It is difficult to go to the theoretical energy required for dissociation L2O3, because you need some energy to keep the bath in hot condition. The bath resistance gives heating. Therefore, you need in theory some energy to decompose L2O3, and then you need some extra energy for heating of the bath. And that is why it is coming down to the minimum, which must be above the theoretical minimum that comes from looking at the free energy of formation. Reduction in net carbon consumption with improvements in cell design. In cell design, the carbon consumption is also going down. That also would mean less generation of CO and CO2. Here is another design of electrolytic cell, which I have shown in connection with some discussions. The cathode anode spacing, this spacing is very critical, 3 to 6 centimeter. The current range is critical. All these are very critical parameters. In reality, we have many cells in series. This is the look from the top, this is the plan view, this is another view of the cell to show that everything is enclosed, because you do not want the gases that come out just to go helter skelter. They all have to taken out very carefully through certain chambers. You see the carbon lining, molten aluminum, on top of that there is the electrolyte layer. I have given some equations to show that not only is aluminum and oxygen released, oxygen becoming CO2, there is also other species that come out, and that is why. Then there is a very interesting discussion I put in, a paper by a man from the industry, because I wanted to show you what that man finds important in the industry. There is a picture of the aluminum electrolytic cells in a long series. That is how an actual plant looks like. They have given some data, talks about what are the important issues, that there are actually plans to recycle 100% of aluminum by 2020. In that case, you do not have to produce aluminum through electrolysis. This may not be possible. It is not a very utopian thing, because aluminum does not get spoiled. So, when a consumer has used aluminum and discarded, it is not going to get corroded. So, it can be in theory recycled, but in countries like India, where we have not reached a certain level of development, we have to keep on producing more aluminum just to satisfy the needs of the classes who are coming up in development. So, we will not be able to recycle the entire aluminum by 2020. Advanced countries should do that. We need technologies to produce non-zero emission from cells. Electrical energy consumption has to be brought down. Then there are some other goals, mostly connected with energy consumption, current efficiency, gas emission, carbon consumption, and the industry is trying to improve on all counts. There was a list of R&D thrusts that I discussed, all related to what I just mentioned, and then discuss the very trick of operation in aluminum cells. There is a very small window. There is a working zone is very small. You cannot increase the bath resistance too much, you cannot decrease it too much. If you decrease the bath resistance too much by bringing the electrodes too close, then there will not be sufficient heating of the electrolyte. If you increase the resistance too much, you will get into a lot of problem, because you might get into operational difficulties. Similarly, alumina, you see the alumina versus cell resistance. If the alumina falls too far below a limit, you will have what we call anode effect. Some gases cover the anode and aluminum cannot be deposited. Then sparks go from one cathode to anode without causing electrolysis, it only causes heating. If the alumina concentration is too high, then it will exceed the solubility limit, it will precipitate out as a sludge. There are all kinds of problems. So, it has to be in a very narrow window of 6 to 8% or something like that. Then the man from the industry has talked about market and demand pull, how the economy is growing, is likely to grow even faster in future. The aluminum demand we think can reach from present 0.7 million tons to 1.1 million next year, 1.7 million tons by 2015. I am sure Mr. Pugajendi has addressed these issues also. Then we have the smelter capacity of some kind. We might have bigger smelters, and we do not design our own smelters. We import designs from abroad, get consultants from abroad. We do not have engineers and metallurgists doing the job for us. So, a lot of money is going out of the country simply for this, and that is why he has listed some ironies, that even if India embarks today to create an Indian specific aluminum smelting technology, it may not be ready by 2015. We do not have our own technologies. All technologies are supplied by leading companies of abroad. Quality manpower is not available. Maybe some of you will go. Incidentally, until recently these companies never paid very well, but now things have changed. The young metallurgists who are joining these companies are being paid very heavily, and I have seen some very young bright boys and girls even willing to go to very remote areas where these alumina smelters are there or leaching the bare process plants are there, because the pay is good, the company treats them well. So, it is a very good option for you, but essentially the emphasis has to be creation of adequate quality manpower, and industry and national planners have to accept that there is something wrong with the present system of giving enough incentives, attracting young people to this industry. I have given in details something about Hindalco, the largest integrated aluminum plant, what they have, what they need. They have an aluminum refinery where power is coming through cogeneration. Cogeneration means simultaneous generation of electricity and steam. You need electricity, you also need steam, which will go for base process. We need a caustic soda plant. You produce caustic soda which will go for leaching. In the smelter also you need power, you need aluminum fluoride, then fabrication rolling mills, all these things they have. You see how the smelting capacity is gradually increasing in our country. We have shown here which all companies are producing aluminum in India and what is their share: Sterlite, Nalco, Hindalco, Indal. This is their production share, this is their market share. Then I ended the discussion by talking about dimensions of future growth. Metal production has to go up, alumina production is going up, rolling capacity has to go up, and some other goals that we have. We gave a cost breakup. The most important thing is to show that according to the figures given, in aluminum production at Hindalco, power is 40% of the total cost, and that you see why aluminum is so very sensitive from the energy point of view. Then there was an analysis of energy consumption, what we can do to bring it down, but companies definitely are trying. That is why the energy consumption is slowly going down, mostly because of the average pot voltage is going down. There is a lot of computer control and other things to make the operations very smooth and standardized, the quality of alumina, quality of bauxite, all the operating parameters. When things are very smooth and standardized and things are controlled, the process controlled by computers and automation, then you can minimize your energy consumption. And there was some data given as to what are the financial implications of slight reduction in voltage, and that is phenomenal. Over the long time, even small changes in power means a lot of advantage in financial terms. These are some data, pot line details. Then there were some challenges for the Indian aluminum industry listed. What are the goals? Reduction in consumption of energy and carbon, indigenous technologies, mathematical modeling, reduction in environmental impacts, increase in per capita consumption, recycling, etc., etc. All these can be done if bright young people come into the aluminum industry. I hope some of you will. Then I have given some discussions on ferroalloys, which I will not discuss now. I will end the discussions here today. Thank you. There are 4 more modules left, 6, 7, 8, 9. I will quickly review them in my last lecture. Thank you very much.